Okay, for those who just came in, I just made an announcement. I will not be here next week, so we will not be meeting during this time. I will be posting sometime between now and next Monday. It may be over the Chinese New Year holiday. I mean, I'm not Chinese, so I don't celebrate Chinese New Year, so that's there. But I always take 2 days off, right? That's there. I'm always geared toward holidays. Although I think we're going to a wedding on Saturday, so I think we're going to Malacca on Friday and Saturday. But still, I'll have time to get this done. That there. Okay, I'm switching gears completely now. That there, and I'm going to talk today strictly about the hardware of the 8086 chip. Now, that is not the chip we're going to be working with, but it's a general purpose microprocessor, which is what this course is supposed to be covering. So we're going to look a little bit at the hardware of this particular chip there. So, and I don't have any preset slides, so I'm going to do what I hate doing is I'm just going to go through the Bry book, which you should found a copy of the Bry book in the on your e-learning. Have you? It's called the 8086 book or something like that. There, have you been able to find that book? Right there, you found that book. All right, so this is the chapter I'm going through is from that book. So, right there, and I'm going to highlight various things, and you'll see this a little bit more on the review sheet because I've got this week to kind of go through this chapter. Right there, the 8086 and the 8088 are the same processor internally, right there. So this chapter talks about the 8086, 8088. Externally, they're two totally different devices. The 8086 is a 16-bit microprocessor, which means that it's got 16 data lines going out. That's there. It's got 20 address lines, and we'll look at those and some of those are shared. The 8088 internally is the same processor. So if I was to go through the first 8 chapters of this book, we'll see that the 8086 and the 8088 internally are exactly the same. They have the same set of registers, the same set that they're. I find that students quite often can grasp the hardware faster than the software, so I'm reversing the order in which this book covers it. That they're to look at the hardware. So the 8088 is slightly different, and we'll look at some of the differences. Now, some of these questions will find themselves on the final, so when you go through the review questions, it's 12:15. Shall we let them in? It's after 12:15, so I'm not sure if we're going to let you in here. That's there. So, okay. These are old processors, so as we go through and look at various things this is kind of the chapter goal, and again, we're going to be looking at these goals as something that's going to be part of what you're going to see on the final exam. So as you look at chapter 9, you'll see right there, describe the function of each 8086 and 88 pin. That's there. Well, guess what? Will probably be on your homework and your final exam will probably be questions, say, define the function of the ALE pin. Right there. So right there is right off the top there. Understand the DC characteristics that indicate it's fan out to common logic. We'll talk a little bit about that. I'm not going to hold you responsible to tell me how many chips can be tied to this in terms of fan out. Does the term fan out mean anything? Ever hear that term before? Fan out? That's the number of devices an output pin can drive before it draws too much current. So, and that's important for a microprocessor and any device that they're. So, the next thing is use the clock generator chip. We're going to talk a little bit about that. I'm not going to really hold you too much to that right there, because clock generator chips are somewhat obsolete. That there. As I mentioned before, the chip you're going to use next semester and the chip we'll be using in our labs is the 8051 clone, and it actually has the clock generator built into the chip. That there. So, as I said, that particular device is somewhat obsolete. That there. When the 8086 was around, we still use that there. We'll look at how to connect buffers and latches to the buses. That's important for whatever processor we're using right there. So we will look at that. This is one that everyone will probably have trouble with, and since I'm recording this, I probably ought to just take my mouse and point right there, is interpret timing diagrams. That there. In your basic digital course, you probably looked at some timing diagrams. When we look at timing diagrams, there's a clock on one, and then the various signals would change with time. We're going to look at how to read timing diagrams. That there. That's an important factor that there. And describe wait states and connect circuitry. Various. That there. We're going to skip that, and we're not going to get a lot into this minimum maximum mode of this chip. That there. So really, we're going to concentrate on the first 5 course segments for the next section of this class, where we talk about the hardware. That there. Yeah. Make sure you keep that little tab in there, or the next group won't get in. The last group was locked out. That there. So, okay, let's kind of go through here, and I'm just going to pull this right off of go through the book here, right here. The pinouts illustration, we'll get into that right there. Describes the pinout to the 8086, 88. There's virtually no difference. Both are packaged there. There are some differences in the control signals. The 8086 requires 5 volts. The 8051 that we're using in this class requires 3.3 volts. So there is a difference between older microprocessors and newer microprocessors. For sake of, if we're talking about the 8086, you have to remember that it's an old processor, it's 5 volts. If we're talking about the Silicon Labs chip that I brought into class, the little board the other day, that's a 3.3 volt chip. So newer processors, newer microcontrollers are different than these older ones. This is a 40-pin IC. It's huge by comparison to today's. It's about this big. I don't have one to bring with me. I think there's 1 or 2 in the lab, but a 40-pin IC is this big. As you look at the one that I passed around in class the other day, and of course, those who are watching the recording can't see that I'm showing it's about 3 inches tall and about 1.5 inches wide. The one that I passed around was about the size of your baby fingernail, right? It was about a 20th of the size, roughly. It's much, much smaller. So these they also required somewhere in the neighborhood of 350 milliamps, which is a huge amount of current by today's standards for a microprocessor. Of course, now the i7, the i5s are pulling somewhere near that, but they're also running considerably faster with a lot more horsepower there. So as we go through and look at this right here, this is the most important drawing right here, and this shows the 8086 in its 2 modes. I'm going to just concentrate on the one on the left, and I'm not going to go through all the pins because some of those are not, I wouldn't say they're not important, but they're not part of the core of what we're going to look at here. So as we look at the left, on the upper left corner there, we see here AD0 through AD7. Whenever you see a line that says AD, that means it's both an address line and a data line. It's so at one point of the clock cycle, the instruction cycle, it's the address line. Later on, it's the data line. So that's a dual purpose bus right there. Same thing on the opposite side of that right there. Over here, we've got A through AD15. Now, when we look at the 8086, that'll be different because it'll only have AD0 through AD7. It won't have the others there. Then we've got below that 4 other lines right here, which is A16/F3 through S6 there. Those are status lines. We won't be talking too much about that, but we'll kind of go through that there. So those are the 8 or 16 address lines, or the 20 address lines and the 16 data lines. This is a 16-bit processor, which means there's 16 data lines. And they're labeled A0 through A15. We also have 20 address lines, A0 through A19. So since it's got 20 address lines, it can address between 0 and 2 to the 15th minus 1, which is right around 1 meg of data. Now, this processor is a very important processor, I should point out, because the original IBM PC, which was way before anybody, 10 years before anybody in this room was born, which is the one that started all the Windows machines before that, the original IBM PC, they call it the 5150 PC. It was about this big. Yeah, it's about a little over 2 feet wide, about a foot and a half deep, 7 or 8 inches tall. It weighed about 25 pounds. Was based on the 8088 right there. So this was the first MS-DOS microcomputer, was based on this processor family. All other MS-DOS machines, when I say MS-DOS, that's before Windows, because they came out with Windows DOS 1.0, 2.0, 3.0, and then 4.0, 5.0. You know, they went various versions of DOS. Then Windows 1.0, which was worthless. Nobody. The first version of Windows that was worth anything was Windows 3.3. So that there, and then the first Windows that didn't have DOS under it was Windows 95. So about the time most of you were born, I don't know, I'm guessing most of you were born about 1995, 93 in that area. It was about the time that Windows became the primary operating system for IBM family machines. That there. So, but every other processor has main compatibility back to this right here. So when we look at desktop computers, they're all based on Intel products, and they all maintained their back there. You could take a program written in 1982, for example, for the IBM PC, and you can run it in compatibility mode on a modern Windows machine. I don't know why you would do that, but you can do that there. So, all right, we've got some other lines over here. One is the clock right here. The other is an interrupt request. Here we've got these MX non-matchable interrupt, a ready line, and some other lines we won't get into. The reset line in order to reset the processor. And somewhere in here there should be an ALE line. Where's our ALE? It's shown over here. I guess we always operate in the min mode. This is the mode that I'm most used to working with that there. So hold acknowledge, hold request line that's going into it right here, hold right there. So this is the mode I'm used to. Let me ignore this one right here. Let's just go to the straight with this one. Clock. A hold line, let me talk briefly about that. It's not used very much. I mentioned the other day that the only device that talks to the address lines is the microprocessor, right? Anybody remember me mentioning something like that? I know I said it. That there. Was anybody awake? Not there. Well, the hold line is a signal that you're telling the microprocessor, some other device, is wanting access to it. And I mentioned some of the early disk controllers, for example, would take control of the address bus and the data lines to write directly to memory. And that was what those lines were for. It was to tell the microprocessor to stop whatever it's doing and let some other device take control of the memory. That there. So you have two lines here, the hold and the hold acknowledge right here. That tells it that the microprocessor is in the hold state right there. So we've got the ready line, the reset line, the test line, which we will talk about the reset line there. And then we got the address latch enable. We'll talk in more detail about that. Interrupt acknowledge, memory IO not. We'll talk a lot more about that. And the read not and write not lines. Those are for interfacing to our memory. Now, a lot of modern processors put that as one line today. Read not and write not. That's put in as one line right there. So these are the pins I'm going to deal with. In the max mode, I'm going to skip that there. So in your little notes memory, that there, keep in mind that all my discussion is going to really gear around the min mode, right there. So maximum mode, minimum mode, right there. Some other discussions right there. I talked about logic levels. I think I said 0.7. This book says 0.8. We're close. 2.0, it's actually more like about 2.5, but we'll get into that there. Logic levels right there. This is getting into the fan out. I'm not going to skip that there. These are these static, these S3 and S4. Those are segment modes. We're not going to worry too much about those static bits for discussion. All right, this is what, if you have one thing to study for final exam, it's this section of this textbook right here. I just mentioned that you're going to see these lines right here. Here, this is the A8 through A15 through A. The 8088, as I mentioned, it only has 8 data lines externally, so it's got those bits that say AD8 through AD15, just say A8 through A15 on the 8088. So that's the difference between the two processors. We're talking about the 8086, so we can skip that one here. Now, let me just kind of read this and explain to you what this says right here. I'm going to go right to the top of the page right here with this. AD15 through AD8. These are the address lines for, and the same thing with AD, it's down 87, that they're composed, the upper 8-bit, they're multiplexed. They contain the address lines A15 through A8 whenever ALE is logic 1, right there. And data connections D15 through D8 whenever the logic lines or ALE signal is low. So that ALE signal is very important because that tells us whether there's an address out there or whether it's data. And ALE stands for address latch enable. That's what that's there. Again, same thing right here. The upper 4 bits of the address are shared with the status lines, which we won't be looking too much at, multiplex signals, also the status bits. These bits also contain a high impedance state there, and they hold acknowledge. Status bit 0 is always logic. We won't get into that there. But typically, we won't worry too much about that. There, A6 through A16 through A19 are just the upper 4 bits of the address for all practical purposes right there. Okay, read is whenever this line is low, that means that the data bus is receptive to data from memory or I/O. In other words, it's telling memory or I/O that it's okay to write onto the bus. Now, which memory location is going to write onto the bus is determined by the address bus. Every memory location tied to this microprocessor has to have an address. Now, a particular IC may have 64K of addresses. It may have 512K of addresses. So we will use something called an address decoder to determine what chip, and then we feed it the rest of the address right there. So we look at this address, and this is very important that we look at right there. So up there, and then the ready is to insert wait states in the timing of the microprocessor. Enters wait state and remains idle. We're not worried about wait states. Now, the interrupt request is used to input a hardware interrupt. It's held high whenever the interrupt flag is set there. It acknowledges it by taking the interrupt line low, right there. Acknowledge low after it's completed. An interrupt is an external piece of hardware that's going to tell the microprocessor to stop what it's doing and do something else. And we have to write code for these interrupts. I look at the interrupt as the check engine light on your car. Something's happened. Although they happen with microprocessors far more often. Something like a UART that's receiving serial data from a terminal will flag an interrupt whenever there's a byte that's in the incoming buffer. If, for example, a key is pressed, that's going to flag an interrupt to the microprocessor saying that a key's been pressed. So we may or may not acknowledge it there. Right there. The test is just used by the wait signal. We'll skip the test. The non-maskable interrupt is that there. So we got 2 interrupts coming into this right here. Actually, 3 is if we count the reset. That there. The non-maskable interrupt is very similar, except for we've got doesn't check to see if the interrupt flag is set to 1. The interrupt flag simply means that our interrupts are enabled so we can acknowledge our interrupts and process them. So we take the interrupt request line high and the interrupt flag is set to 0, that means that we're not acknowledging any interrupts. We basically put the do not disturb sign out on the door. The non-maskable interrupt, there is no do not disturb sign right there. We cannot ignore that one right there. So we have two types of interrupts, a maskable interrupt and a non-maskable interrupt. Again, that's a key question. What's the difference between the two? The name should give you a hint. You can ignore a maskable interrupt by setting the interrupt flag to 0. That means that all interrupts are enabled coming to the interrupt request. We're not going to process. And there's times we want to do that. If we're doing something, timing is very critical with our processor. We don't want it to be interrupted because we're counting down that we're doing something. The non-maskable, it means that something bad is happening. A heat sensor, that there might go to a non-maskable. We don't want to ignore the fact that the room has gotten too hot, might be on fire, right there. The reset line is one that does exactly what it's supposed to do. It resets the processor. Now, we actually have to put some hardware into our processor. Usually it's just a little resistor capacitor network in order to ensure that that line is taken high for a minimum of 4 clock cycles. Most modern processors actually use a interrupt not right there. Okay. The clock signal provides basic timing. You must have a duty cycle of 33% right there in order to ensure proper timing. Right there. So that's part of the, you can't use just any clock signal. It's got to have a 33% duty cycle to it or else it doesn't work properly. Right there. As we go through right here, our VCC is self-explanatory. That's the power. All digital ICs have VCC to them. Right there. And the term VCC actually stands for collector-to-collector voltage. Right there. That's where that comes from. Ground, you sometimes see VDD or VSS or VEE instead of ground on some of these data sheets. VCC is pretty much understood. That's the voltage at the collector of a transistor that's always tied to the high rail. If you look at a transistor, quite often the emitter is tied to ground, so they'll call that VEE. Or if it's a MOSFET, they might call it VDD, right there. So you might see different terms, but basically it's ground. There are 2 ground pins on the 8086 right there. So the min-max determines whether or not it's in the minimum or maximum mode, and the high bus enables use right there is to enable the most significant data buses, 0 read or write, right there. So in other words, that basically says that we can, with the 8086, we have the option of doing 8-bit instructions, where we're going out and we're only going to read 8 bits instead of 16 bits. So if we're going to go through, if we set this line high, that means that we're going to be doing a 16-bit instruction versus an 8-bit instruction. That's there. And that's usually, again, part of that discussion right there. Now, some other pins. We're going to spend most of the hour just reading through this pin list, but that there. But you have to know this pin list. That there. So it's right there. Right there. So these are the ones that the minimum mode, and that's the mode that I'm going to be testing you on. Is the minimum mode right there. IO/memory not or memory/IO right there. This pin indicates it's going to either write or it's going to read right there. So basically, excuse me, IO memory not. I'm getting ahead of it there. I'm looking at read not, read write not. IO memory not means that we're either talking to an IO or a memory device. Now, this is where things get really confusing to somebody first dealing with microprocessors. When we hook up I/O devices to our microprocessor, we can connect them to the microprocessor as output ports or input ports, and which means that they use addresses the same as memory, but they're in a different address space. They're overlapping right there. So we can have a device on port 25, for example, and a memory location 25, and they're two totally different memory locations. The I/O might be, for example, a 8-bit input. If I'm talking to the I/O device, I'm going to take that line high right there. Or, excuse me, I/O, I'm going to take it low. And right there. And don't ask me why they did this. This is the mystery, one of the mysteries of Intel, is that they reverse those two chips on the 8086 and the 8088. That pin, if it's low on the 8086, that means we're talking to an input or output device. If it's high, we're talking to a memory device. It's the reverse if you're talking to the 8088. So even though the two chips internally are almost the same, or are pretty much the same, externally they're very similar, they reverse that particular pin to really screw up engineers. And I know a lot of, not just students, but real working engineers have gotten hung up on this right there. They're used to dealing with an 8086, all of a sudden they're on a project using an 8088, it's the same chip, no problem. They wire it up and they fail to realize that line's been reversed. That's one of those gotchas in the data sheet. That there. And that there. So that's a confusing line right there, and that's why I want to kind of highlight that there. A lot of hardware engineers don't want to be bothered with this line. So what they do is they just take some of their memory space and say, I'm going to put all my I/Os, up in this memory range, and they use the same memory space as the memory, or the same address space as the memory. So you'll hear the term. Well, you might not hear it. I've heard it a lot, but depending if you end up working around this industry, you'll hear something called memory mapped I/O. Memory mapped I/O means that they've taken the memory or the I/O and they put it within the memory addressing space. So they ignore that line right there. So there are some advantages to it because there's more instructions available for writing to memory than there is to I/O ports. That there. Plus, you've got more address space for I/O than you do, or for memory than you do I/O. But you also, so there's some advantages and some disadvantages. So, but again, this is that there, the write not line, and there's another one down here, read not, right there, indicates the 8086 is outputting data to during this line, it's a logic 0, right there, means it contains data, and it floats to a high impedance here and hold acknowledge. So what this simply says is, the first thing that the microprocessor does is it puts out an address, and then it takes the ALE high, and we're going to look at these timing diagrams. Once it puts the address out, and if it's the microprocessor's writing data out, it's then going to put this write line low, saying that I'm writing there, and that tells whatever device out there that there's valid data there. This is part of the control, and it controls the timing of what goes on. Because you got to remember, you got to put the address, then you got to put the data. Once the data is there, then you got to tell the device to grab the data, and that's what that write not line does, right there. The interrupt acknowledge is a response interrupt that's normally used to gate the interrupt vector onto the data bus in response to an interrupt request. What happens, again, this is getting a little deeper, we're going to see a lot more of this, is a device requests an interrupt, the microprocessor acknowledges the interrupt, then that device then writes to the data bus what the interrupt number is, what type of interrupt it is. Because we got one interrupt line, and we can have hundreds of different types of interrupts. So we have to know what type of interrupt it is. And so what this line does is this is telling is a response to the interrupt input pin is normally used to gate the interrupt vector number onto the data bus in response to an interrupt request. So I have a sensor out here, a pressure sensor, and it goes over the known pressure. And I set that pressure to interrupt number 23, and I'm picking a number right there. So that pressure sensor goes high, it sends a request to the microprocessor saying that I've got an interrupt for you, and it does that on an input pin called interrupt request, INTR. The microprocessor comes back and says, okay, I acknowledge your interrupt. Now tell me what type of interrupt it is. And now my pressure sensor logic would then put 23 onto the data bus so the microprocessor knows what type of interrupt it is. And my code then would then call the interrupt service routine, which we haven't talked about because we're into hardware versus that, but it does the code to handle that interrupt. You know, so anytime there's an interrupt, we have to be able to, we have to have a piece of software to handle that interrupt. You know, and I look at that as, for example, a nurse's station. If you got a nurse that's sitting there at her cubicle, you know, reading some, you know, I'll use American nurses. I don't know what Malaysian nurses do at their cubicles. My ex-wife was a nurse, so I know exactly what they do. They sit there and they read trashy romance novels. That's there. They have nothing else to do. They're sitting there reading this novel. And they're male nurses too, so I don't know what they do. I wasn't married to a male nurse, only a female nurse. That's there. But regardless, they're sitting there reading that, and a buzzer comes on. Well, the first thing they're going to do is they're going to clear the buzzer, and they're going to go ask the patient or go into the patient's room to see what needs to be done. There's a set protocol that they go through depending on what the interrupt is. I mean, it happens to be the IV machine is out of fluid. You know, they will turn the IV machine off and hang a new bag of plasma or whatever they're injecting into the patient. If the patient's morphine push button's been pushed too many times, it's out of morphine, they'll go and scold the patient for seeking too many drugs. That's there, or whatever. But every interrupt has a protocol that has to be done for it. That's there. And we have to, as engineers, we have to anticipate what interrupts there are and write the routines for that. And of course, we're going to know what interrupts they are because we have to design the hardware to generate the interrupts. So we have to know, for example, if it's a high pressure, we may open a valve to release the pressure. If that doesn't release it, we may open another valve. In other words, we have various things we're going to do to solve this hardware problem. And that's what this interrupt acknowledge line is part of that system. The ALE, I keep talking about that. The address contains valid address there. It can be address, it's either a memory or an I/O port number. So that's part of, the microprocessor is written onto the address bus. a valid address, and it's just saying, all right, there's a valid address out there, latch it on, right there, right there. All right, these are DT and R not data received signals they are part of the serial interface to talk to other devices. We'll get into more detail on that later. The data bus enable activates external data bus buffers. We'll get into more detail on that there. The hold, I mentioned, the hold acknowledge is for direct memory access. Right there, I've talked a little bit about that before. Again, those are certain types of devices we'll want to talk to the memory directly and take the microprocessor out of the loop. Right there. We won't be dealing with any of those in this class. I just want to point out that they do exist. Some of the early graphics cards use that. In other words, if you wanted to show an image, you'd dump it into memory, and the graphics card would grab it from the memory and send it right to the display and bypass the processor to speed that process up. Right there. Now most graphics cards have their own memory internal, and they don't share the graphics with the actual computer system. If you look at a modern graphics card, it's got 512 meg, 1 gig, 2 gig. I think I've seen some 4 gig memory or graphics cards out there. Usually the gamers play that. How many gamers do we have? No one's going to raise their hand and say they play video games. Your friend's pointing to you and saying you're a gamer. That's there. That's there. Gamers typically have high-end computer systems simply because of the graphics requirements. That's there. So that's there. All right. that's all the pins I want to go through on the 8086 right there. I'm going to skip the maximum modes here. So I'm just kind of going through this chapter right here. That there, because you can see it gets into a lot more detail when we get into the max mode. The max mode, by the way, the maximum mode is used predominantly, if you read this right here, in order to achieve maximum mode for use with external coprocessors. That there, if we're using this 8086 with other microprocessors, we'll quite often use the maximum mode in order to talk to other processors. At the time the 8086 was out, there were a couple of what they call coprocessors produced at the same time. Those have since gone away. There was the 8087 math coprocessor, there was the 8089 graphics processor. These were processors you would put in your computer with the 8088 in order to speed it up. Almost every engineer I knew had the math coprocessor next to it. Starting with the 486, they built the math coprocessor into the processor. So you don't have the coprocessors anymore, right there. They're now part of the main processor. But the math coprocessor got you interesting instructions in your instruction set, such as sine and cosine and tangent, square root. They expanded the instruction set to include a lot of mathematical functions, right there. So I'm not going to. This is a first semester course on microprocessors. We are not going to get into code processing, right there. Okay, I'm going to talk a little bit about this chip right here. I'm not going to dwell on it much right here because it's not used much anymore, but it's part of the objectives of this course that I have to at least mention it. That there. This is the clock generator. How am I on time? At 1 o'clock I'm going to reset my recording here. The clock generator, essentially what it does is it generates the clock signal required by the microprocessor. The 8086, as I said earlier, and that's a quiz question, by the way, what is the duty cycle for an 8086 clock signal? 33%. You're going to have a whole list of about 100 of these questions coming up that you're going to have to look at right there. But it requires a 33% clock square wave coming to it, and it's basically going to be generated by this chip right here. Auxiliary component without there. You have to generate many additional circuits. At the time, this was the easiest way to do it. When I say at the time, I'm talking 1980. That was long before any of you were even thought of that there. It was very early in my career. Actually, I was still a student in 1980 when this chip came out. This was the most efficient way to generate the clock, was to use an 8224 or 8284. Where did I get this? There are so many of these chips I used to know them off the top of my head. I haven't used this chip in probably 20 years. That tells you how old it is. But what this chip does is it generates the clock coming out for the microprocessor right there. It's got a bunch of inputs coming to it right here. I'm not going to spend a lot of time on that because it's really a waste of our time to spend a lot of time on it, other than the fact that it did exist right here. This book goes through all the pins for it. I am not going to hold you responsible for all the pins right there. The only one that probably makes that there is the crystal. If you look at the 8051, I had its pin up the other day. We'll come back to that later in the semester. That particular chip had no clock. It had 2 input pins that you could or could not hook up to a crystal if you chose to, or a clock input. You could use an external clock with the 8051, but it had the clock generator internally, right there. It's part of the chip. They basically took the 8284 and stuck it inside the chip, right there, and removed the need to have it external. And they also did it in such a way that you didn't need the crystal. But you could, if you wanted very accurate, right there. But this whole purpose of this chip here is to just generate a signal right there. You can see it's got all kinds of pins. And there's the internal workings of this thing. as you can see, it's a fairly complex device right here. It's got a reset request. It has a reset going out. It has an oscillator going out. Here's the clock going to the microprocessor. This is the ready line. It's got all kinds of things here. Typically, this is the way it was set up. That there. This schematic, by the way, is still a valid schematic here on the left, right there. And you will be required to know that schematic right there. And we'll go through that in more detail. This is a standard reset schematic. Every microprocessor, every microcontroller has a reset circuit there. Now notice that I said it's normally a reset not on most microcontrollers. Coming in 8284, it went to the reset not. What this is when I first power this circuit up, this capacitor is discharged. And I don't know if I can write on the screen or not. Right here, yeah. I gotta hit the escape button. Tools. No, this one doesn't let me do that up there. Okay. Okay. Okay, let me just kind of go through this circuit briefly. This is 5 volts or 3 volts, depending on the microprocessor right there. Typically, sometimes you'll have this diode, sometimes it's left off right there. That's just basically to prevent power surges from getting back to there. We have a capacitor here, right here. We have a ground here, and then we have a push button switch right here that goes to ground right there. And what happens when you first power this up is the voltage across this capacitor right here. This is a simple RC time circuit. You should have had it in circuits 1, that when you first power this up, the voltage of the capacitor is going to go from 0 to 5 volts or 3 volts, and it's going to take from here to here 5 time constants, 5 times tau right there, the time constant. And the time constant tau is equal to RC right there. That's how, up there. Well, somewhere right around here is our 2 volts in order to go from low to high right there. So what this ensures is that it stays low long enough to reset the processor. And then it floats high in order to keep from resetting the processor later. If I push this button, that's my reset button, I take it back, you know, it's sitting here, it's high, I push that button, and that takes it low again, I release the button, and it goes high again. That's all that does. And that just resets the processor is what that does. And that's the reset button you'll find on a lot of devices. You know, there's a little tiny button on the bottom. You can take a paper clip in and press, or whichever. But this is the reset circuit right there. Go back to read mode. So what I try to show the diode backwards. I typically never put the diode in there. Right there. But that's our reset circuit right there. And you will be expected to know what that is. The clock generator, I don't worry too much about. Right there. You know, we put this thing into a particular mode, So as far as inputs goes, there's only two inputs that we worry about. That's our crystal. This sets our frequency in which our microprocessors can operate at. This is a 15 megahertz processor right there. This does our power on reset and manual reset right here, right there. Ignore these pins. And we only have coming out of here is our reset going to our system reset, and our this is divided by 3. It's a 5 megahertz clock right there. Right there. It needs that 15 megahertz because remember it's a third clock cycle. So for the first clock it's high, the next two is low, high, low. So it needs a 15 meg. This crystal has to be 3 times the frequency right there in order to generate that 33% clock cycle right there. So that's our right there. I'm going to go ahead and just reset this right here. Give me a minute. I always have to do this right here. Otherwise this file becomes too large.